So this P6 video is on half-life. The definitions involved using graphs to find half-life and the calculations you need to be able to do. So first of all, what is half-life? Well, to understand it, we need to remember that radioactive decay is random, which means that we cannot predict when an individual nucleus will decay, but we can say what the chances of it decaying are in a certain amount of time. And that random nature leads to a pattern that we're going to see in a second, which lets us define half-life. Radioactive decay is also spontaneous, which means that we don't need to do anything to make it happen, it just happens on its own. Okay, so the half-life is defined as the time it takes for half of the nuclei in a sample of a radioactive isotope to decay. Now that's not a very practical way of measuring half-life because we cannot count the individual nuclei in the sample. So the practical way to measure it is to measure what we call the activity of the sample, and we can redefine half-life as the time it takes for the activity of the radioactive sample to halve. So what activity is the total number of decays per second inside the sample, and that uses a unit called becquerel, where 1 becquerel is 1 decay per second. So when you put a Geiger counter or a Geiger-Müller tube near to a radioactive sample, you are actually measuring a fraction of those decays, because not all of the decay products go into the Geiger-Müller tube. But as long as you keep the Geiger counter at a fixed distance, then your decay rate from your sample, so your activity of your sample, will be proportional to the counting rate on the Geiger counter. So we can still use it to look at the pattern of decay. So what does this pattern of decay look like? Well, if we have a time axis horizontally on our graph here and a count rate from the Geiger counter on the vertical axis, then the decay pattern looks something like this. This is what happens. So in this particular case, we've got a count rate of 600 becquerel to start with, and all we do to find the half-life is we read off the graph at half of that value. So we go down to 300, across and down to the time axis where the read-off hits the curve, and that clearly here gives us a half-life of 4 hours. Now to confirm that, right, we can keep going, so we can halve that 300 to get to 150, read across again, and now you can see we're at 8 hours, so we've got another 4 hours for it to halve again. And you can keep doing that, half it down to 75, and you will get to 12 hours. So each of those time periods is a half-life, so the half-life in this case is clearly 4 hours. That's how we read half-life from our graph. Okay, so what about the calculations you might need to be able to do? Well, there's kind of two types. There's one in which you're asked to find an expected amount of activity and given the half-life. So let's see how to do that one. So a radioactive isotope has a half-life of 30 minutes. A sample has an initial activity of 2,400 becquerel, or 2,400 counts per second. After 2 hours, what's the expected activity? So if you get a question like this, remember there are no formulae on the formula sheet for this. You just have to remember what to do. All you need to do is to work out how many half-lives the time period corresponds to. So that's step one. And here we've got 2 hours, and 30 minutes goes into 2 hours 4 times, so we've got 4 half-lives. Step 2 then is just halve the activity you started with that number of times to get the final activity. So we've got 4 half-lives, we need to halve the activity 4 times. So starting from our 2,400, we halve it once, which takes 30 minutes to get to 1,200. Twice, another 30 minutes, so an hour in total to get to 600. Another 30 minutes, or an hour and a half now to get to 300. And then a final 30 minutes, giving us the total of 2 hours to get to 150 becquerel. So that's our final activity. Another type of calculation they can ask you to do is they give you, instead of telling you what the half-life is, they give you a starting count rate and a final count rate and ask you to find the half-life. So the approach is kind of a little bit backwards to the previous one for this one. So in this example, we've got a radioactive sample, initial activity of 10,000 becquerel, leave it for 9 days, and the activity is dropped to 1,250. What's the half-life? So this time, what you do to start with is you just halve the initial activity until you get to the final activity. So you just keep halving it. So 10,000, halve it once to 5,000, again to 2,500, and then finally to 1,250. And the same way as before, each of those arrows represents 1 half-life, because that's the time it's taken for you to halve the activity of the sample. So all you do now is you count the arrows, and then set that number of half-lives equal to the time period you've been given in the question. So we've got 3 arrows here. That means 3 half-lives is equal to the 9 days we've been given in the question, and therefore the half-life is 9 over 3, 3 days. Okay? So those are the two broad types of question that you might be asked. There's one little thing just to be careful about, which is the idea of background radiation. If you remember that background radiation comes from lots of natural and man-made sources, things like radon gas, rocks around us, food, cosmic rays. Medical uses mainly is the main artificial use, but this is everywhere and it's kind of constant. It just stays in the background. So if you are doing any measurements of count rate, you should really measure the background count first, so without the sample there, and then whatever activities you measure for your samples, you need to take the background count away. So just have a look at the previous question again, but this time with the background count added on, so you can see how we get how we put another step in to get rid of this problem. Okay, so same question as before, but I've tweaked the numbers slightly and told you a background count. So radioactive sample this time, initial activity of 10,500, after 9 days it's 1,750, but the background count rate is 500. So we just do the same as we did before, but before we do anything else, we just subtract the background count off of the numbers we've been given. So our initial count rate then becomes 10,500 minus 500, which is 10,000, and the final count rate comes 1,750 minus 500, which is 1,250. And then the problem can proceed exactly as we did before. So you just have to remember to subtract that initial background count rate off. If you forget to do that, you may find that the halving never gets you to the right value for the final count rate. So if that happens, do just check that there's no background count you'll be given in the question, because you might need to take it off first. So that's half-life, what it is, how to find it from a graph, and how to use it in calculations.